So well, up to now we have discussed about VBT, valency band theory, VBT. Now we will try to understand this concept of VBT by taking various examples. So as discussed earlier, according to valency bond theory, generally in the formation of the complexes, the central atom should be able to provide the required number of the vacant orbitals. So after providing required number of vacant orbitals, so definitely these vacant orbitals will undergo corresponding hybridization to provide the corresponding number of the hybrid orbitals. Now the ligands which have the lone pair of electrons, so they donate the corresponding lone pairs to form the corresponding complex compounds. So let us see various examples to understand this valence bond theory. We'll start with tetrahedral complexes. Tetrahedral complexes. So in this complexes, as we are aware, so definitely the central atom should be sp3 hybridized. sp3 hybridized. That means it is able to have the vacant orbitals. So these will undergo hybridization to give correspondingly 4 sp3 hybrid orbitals. So these will accept the electron pairs from the ligands, so that the resultant geometry of the complex will be the tetrahedral geometry. So let us take for example nickel tetracarbonyl. Nickel tetracarbonyl. So here the central atom is nickel. So it is of 3D series element with atomic number 28. So coming to the nickel here, so nickel have the argon followed by 3D8 4s2. 3D8 4s2. So this we can write like in the orbital form. So 3D orbitals, there are 5 3D orbitals and one 4s orbital. So D8, that means we will have 1 2 3 4 5 6 7 8. This is a 3D8 and 4s2. This is in the ground state. Of course it is having the 4p orbital as a vacant. This is the 4p orbital corresponding this nickel. So it is having 8 electrons in the d orbital, which is 3d orbital, and 2 electrons in the 4s orbital, and the remaining come across these will have the vacant, which are 4p orbitals, 4p0. Now here the oxidation state of this nickel in this particular complex is 0. The oxidation state of the corresponding nickel central atom is 0 in this particular complex. And here coming to the carbon monoxide CO, this is a ligand. So here this ligand now should donate the electron pairs to the central metal atom, that is the nickel atom. So definitely in order to have or in order to form the complex compound, so definitely the nickel should provide the corresponding vacant orbitals. So in the presence of the carbon monoxide, actually the carbon monoxide is generally called as strong field ligand or strong ligand. In presence of the strong field ligands, generally what happens is the corresponding electrons will undergo pairing. So that's why in presence of the carbon monoxide, what happens is this particular 2 electrons which are present in the 4s orbital shift onto the corresponding 3d orbitals. So because of this reason, so in presence of the ligands or in presence of carbon monoxide, which is a strong field ligand. So in presence of this, so these electrons will shift on to the corresponding 3d orbital of the nickel. So therefore the configuration we can see here, this will be completely filled with 2 electrons each. That's why here we have 4s orbital, it is now vacant. This 4s is vacant, and also 4p orbital is also vacant. So because of this, now we have 4s and this is 4p. So totally we have the corresponding 4 orbitals. Now these 4 will undergo hybridization to give the total of 4 sp3 orbitals. 4 sp3 orbitals. That's why if you see in overall here 1, 2, 3, 4 sp3 orbitals will be formed. Now we can show the same thing like this. Yes, this is a 3D which is filled completely, and sp3 hybridization. So because of this, you can see all these 4 are sp3 orbitals. sp3 orbitals. Now each carbon monoxide CO will provide 1 electron pair. So that's why, so it can form, this is the 1 pair given by 1 carbon monoxide, another pair given by another carbon monoxide. Likewise we can see the pairing of the corresponding, or we can show this in dotted with. So this is another carbon monoxide, carbon monoxide, carbon monoxide. So this is providing 1 lone pair to this, other is providing another lone pair. So all these 4 are able to provide the corresponding lone pairs, so that the nickel tetracarbonyl complex is formed here. This is, now see the geometry of this. So this is a tetrahedral geometry. So nickel, the central atom. So here you can see here, this is 1 CO and another CO, and we can also see CO, and this is another CO. We can see this as tetrahedral arrangement of the corresponding case, nickel tetracarbonyl. At the same time, if we see this particular complex, we cannot find any unpaired electrons. That's why if you see the magnetic property of this nickel tetracarbonyl complex, so this is a diamagnetic substance. So because when I come across about the magnetic properties, the complexes or the compounds which are having unpaired electrons generally shows the paramagnetic property. So whenever the complexes or the compounds having the unpaired electrons, so they will be paramagnetic in nature. And here whenever the electrons are completely paired in the corresponding complex or the compound, they show the diamagnetic property. So that's why this corresponding nickel tetracarbonyl, if you come across, this is a diamagnetic substance because of the absence of the unpaired electrons. Otherwise all the available electrons are paired up. So this you can see about the tetrahedral complex of the corresponding nickel complex. And apart from this, we can also take another example like nickel NiCl4 minus 2. Here also you can see the hybridization as sp3 hybridization. So definitely the geometry will be tetrahedral. So it is a tetrahedral complex. So likewise you can take various cases. Anyway, this is how we can understand based on the valence band theory how the tetrahedral complex is formed with suitable example of nickel tetracarbonyl.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.